Swayam Prabha. Digital India. Educated India.
In the previous lecture, I have been talking about the constituents of soils, and we described different phases which are present in the system, soil system, and I have been discussing a bit about the particulate nature of the soils. And this is where I gave an analogy that soils behave both ways, they act like fluids, they act like solids, and this is where the subject becomes very interesting, because there is something in between the fluid mechanics and the solid mechanics. In context of this, I was defining what the particulate system is all about, and just to reiterate, the particulate system is a system of the material which is consisting of particles. Sometimes we call them as grains also. So, I have been talking about a situation where you have a control volume, and this control volume is confined in such a manner that the boundaries are rigid. So, AA and BB are the boundaries. And these boundaries are confining the material. For the sake of simplicity, I am assuming granular material, and I had talked about the micromechanics of the system. There is a piston, and through which I am applying the normal stress sigma. So, this part we have already discussed, that if these boundaries are rigid, there is not going to be any lateral deformation, and we had also talked about the mechanisms of deformation. That is the crushing of particles, the second mechanism which I discussed in detail was the bending, and the third one is the rolling. Alright, and this is where our assumption was that if the soil which is particulate in nature is confined within the rigid boundary system, is compressed, then the deformation is going to be guided by these three mechanisms or the combination of these three. Alright. I had also introduced here the concept of stress and strain, that if I magnify this system, this is how it would look like. You have a grain which is in touch with another grain, and because of the normal stress which you are applying over here, there will be a normal component of the stress, sigma x, let us say, or whatever. This is different than sigma, so let it be sigma x, and there will be a shear stress. The moment shear stress gets bigger than the tau of the binding, or what we call as the, let us say, the cementation, that is the particle, the cementation which is surrounding the particles, we talked about this, which gives the cohesion of the material. So, the moment tau is greater than tau cementation, there is a rolling over which is occurring, the mechanism 3 takes over, but this is going to be very minor because the boundaries are rigid. So, truly speaking, in most of the situations as we were discussing in the last lecture, the chances of AA and AB being rigid are extremely less, unless you are working in a casing system. Let us say I gave you an example of bridge piers, where you fill up the cylindrical portion with sands and then let the foundation of the bridges sit over there. The second mechanism would be when the boundaries are flexible, and this is where exactly I was in the previous lecture. Now, the chances are that the boundaries which are confining the soil mass would be flexible. Now, in this case, sorry, one more thing you should add to this is that this is what is going to cause the volumetric deformation. Alright. However, when the system is flexible, the mechanism 3 becomes more prominent, predominant you may say. Alright. So, it so happens, stop writing and just see my hands, the way I will be using my hands to depict what is happening. When you are applying normal stress on the system and the boundaries are flexible, it is just like balloon, you keep on pumping in air and what happens, the balloons, it keeps on expanding. So, what is going to happen is AA and AB are going to get deflected much more, and because of that there would be a flow of material in the lateral direction, alright. So, this is what is known as a flow. Until now you have used the flow of the material in case of fluid mechanics only, where the fluids flow. Now, this is the first time we are trying to use this term for a granular material which is soils. So, granular materials also flow freely. This concept I will be using in the second course when we talk about the shear strength of the materials, fine. So, this is what is going to be flow process. The applications of this concept would be when you are designing warehouses, particularly when you are filling the sands, for creating the pads of different types, where you allow material to just flow in and then you compact it. This is a good example of silos which are normally designed for keeping the grains, any type of grain, let it be wheat, rice, sugar, whatever. So, these concepts are used when we design the silos, alright. So, here the material is flowing, in this case the shear strength is going to be predominant. So, this becomes a shearing process. Check out on net, when shearing process occurs in natural systems like active faults. A good example would be, I am sure in engineering geology course you must have studied, there is a ground like this and there is an active fault over here. I am sure you must be aware that the Bombay is sitting on 3 active faults, and that was the main challenge in designing the Bandra Valley sea link. So, read the history of what these faults do. Now, suppose if I load this system from the top and this fault opens up, this is a geological process, and because of this tsunamis come, because of this earthquakes may come and whatever. So, what is going to happen is that this portion of the soil or the rock is going to shift downwards, clear, and this is how the movement is going to take place. So, there is a relative movement along the surface, which is, let us say, I would define as 1 1. Is this part clear? So, the moment you load it from the top and if there is an active fault, the whole thing may slide down. In the process, on this surface the shear stress develops. Beautiful application of the engineering mechanics which you have done until now. You must be wondering where are you going to use the concepts of engineering mechanics. This is one of the applications of where mostly the guys who are in petroleum geophysics would be very eager to understand what type of stress are going to act, what are the lateral stresses, and under what circumstances this type of conditions are going to occur, alright. So, for the time being I am not going to go into the details of this, because this is a topic which I will be covering in geotechnical engineering 2. I will be dedicating a lot of time on this. So, coming back to the point, when soils are confined depending upon the boundary conditions, is a simple explanation of a mechanism where we deal with the rigid and the flexible systems. A rigid system yields the deformation of the soils provided 1, 2, 3 or the combination of these 3 is occurring, or it could be because of the flow process, and which is a beautiful example of shearing process. Now, if I want to complicate this system, and if I say that rather than having this as a granular material, suppose this material also has cohesion, alright. So, the first question is, how would you differentiate between granular material which is giving you friction component of the strength and the cohesion component of the strength. This again we will be discussing in the second course, alright. This is beyond, because first we have to understand the material itself. So, in this course geotechnical engineering 1, our understanding or maybe the more emphasis is to understand the material rather than going into the shear strength characteristics. Now, one interesting thing which I can derive from this whole discussion is the constitutive law. So, many of you would be working on the application of constitutive laws in mechanics, particularly in geomechanics or whatever. Truly speaking, constitutive law is a relationship between stress and strain. You have studied this earlier also in 10+2 physics, is it not? You know how the stress and strain vary, and then coefficient of this function is normally defined as elastic modulus. Sometimes we define this as Young's modulus or whatever, depends upon the material, alright. Now, in this case, when we are dealing with the granular material, this function is going to be a nonlinear function. Now, this is what is known as material nonlinearity. So, those of you who might be studying FEM, finite element methods and all, would be using these concepts quite a lot. So, the material is nonlinear. Why? Because of all this. It is not a linear material. A linear material would have been something like this. This is a linear material as far as the stress strain properties are concerned, okay. So, by virtue of all these particulate system, the material behaves as nonlinear, and hence it becomes very difficult to determine the stress strain relationship, though there are several tests which we will be talking about again in the realm of shear strength theory, alright. Any questions here? The slope of this line could be the elastic modulus. We normally do not use the term y as the yield modulus over here. It's okay. Any question?
Sir, you told the flexible part has the predominant of rolling of the particles, but how we call them as a flexible if it is rolling?
No, boundaries are flexible. Imagine, when you go to the villages, what people do is they will be taking a container and they pour some material like wheat or whatever, and they use a, what do you call this, it is a wooden tamp normally, I do not know what is the local name, and what do? They just keep on tamping it to densify it. Is this correct? So, imagine if the boundaries, if this was a container made up of rubber or plastic, thin plastic, what would have happened? So, the moment you tamp it from the top, it would deflect in the lateral direction, clear. So, this is what the mechanism is. So, when the boundaries are flexible, the material is more free or prone to flow outside. It's okay, and the process is because of the rolling. So, if you remember the basic model which I had drawn last time, you have a set of particles, and suppose if I press it from top, what is going to happen? The chances are that this particle will slide over and it will acquire a new position like this. What will happen to this? This will also slide over, it will acquire a new position like this. We will discuss these things in detail. Is this okay? Conceptually, are you able to visualize? So, everything is being restrained by the boundaries.
So, what is the difference between cohesion and friction?
These are the two components of the shear strength. So, shear strength can be mobilized either by ways of friction of the material or because of the cohesion. Material would behave either in a cohesive manner, uniform material clays, they are mostly cohesive. So, you press them, the shear strength is because of the cohesion. Granular material, sands, alright, you press them, the shear strength is predominantly because of the friction. Do not bother, we will discuss this later, clear. And I am not going to draw these most of the figures which are normally used to describe the structure of soils, or the grain structure sometimes is also called as. So, this is also described as the grain structure. Soil being a particulate material, all the properties of the material are dictated by the way it is formed, deposited, clear, and that is what is known as structure. So, what I suggest is that you please refer to a book, particularly Craig, which I said, try to follow what I am projecting here. I will try to explain you as much as I can, but you have to ultimately put it in your memory, because this is what is going to be fundamental aspect of the soils which we will be using quite a lot. So, when we talk about the structures of the soil, this is also known as grain structure, alright. Basically what it defines is the arrangement of the soil grains. Weathering takes place, there is a transportation agency, and then ultimately these grains of the soil which have become very fine, they come and settle down somewhere. Now, what happens is, why this is very important to study is because grain structure is controlling all the engineering properties of the soils, alright. This will control each and everything. So, this has a strong bearing on most of the mechanisms. Any process which occurs in the soil mass, and soil mass is nothing but consisting of millions of discrete particles which are particulate materials, alright. So, what happens is the structure of the soil is going to control the strength, permeability, any type of permeability, hydraulic conductivity. Hydraulic means water, fluid conductivity, gases, crude oil, alright, different type of contaminants, compaction, compressibility, shear strength, consolidation, everything. So, henceforth what I will be doing is, it is just like understanding somebody from the very early childhood. So, once you understand this boy or girl is like this, you can handle this person carefully, and you understand maybe 85% of what this person is going to behave like, alright. So, that is why this is important. Now, it so happens the first type of structure which we normally talk about is single grain structure. We call it as single grain. Body forces are predominant, individual particle has weight, and hence the stacking is going to be something like this. So, what I have shown over here is a single grained structure. Each grain is so important that it contributes. If I take out a grain, clear, or if I take out several grains, maybe after 3-4 years when you become an expert in soil mechanics, you will try to model a tunneling process over here. So, tunneling is nothing but removing the soil mass slowly and slowly and creating a tunnel, clear. So, we can model these type of concepts by removing the elements the way we want. So, this is a typical single grained structure. We also call this as coarse grained materials. The another variety of the soils which we will be dealing with would be fine grained materials. Normally the particle size are more than 20 microns. What are the properties of this material? The gravity predominates. We also call them as body forces, alright. So, when the settlement process takes place, the settlement of the particles to form a deposit is because of the gravity. There are no other body forces which are acting on no surface forces, not body forces, surface forces which are not going to act on this. So, the body forces predominate over the surface forces. Grain to grain contact is very important. So, what is that you are talking about? You know, 2 grains, just do a simple example. You take few grains of the sand and just rub them, sound comes, clear, and you feel that there is lot of friction which is getting mobilized. So, this is the mobilization of the frictional strength, alright. When you take a clay, you do the same thing, it might stick in your hands, clear. So, that is cohesive strength. So, this is grain to grain contact, continuum mechanics, read about continuum mechanics. Now, these type of depositions are either in very loose state or in very dense state. So, today we are going to discuss about how to quantify the dense state and the loose state of the material. When we say loose state, it is a very high void ratio, both are correct, void's ratio is also correct, void ratio is also correct. So, do not get confused by the term. Loose state is the one where the void ratios are extremely high, dense state is the one where the void ratios are less, clear. I gave you some example how deltas were formed. So, next time or maybe dig out the movies from the National Geographic and try to see how the delta formation takes place. The beautiful example of delta formation, the mechanism which controls the entire deposition of the sands would be grain to grain structure, is it not? The body forces are creating a sort of a assembly of the single grain particle. So, when you have salt water, fresh water bringing lot of sediments, there is a density contrast, the suspended particles cannot bear the density contrast, they just deposit over there, and that is what is happening over here, alright. By virtue of this structure, either the permeability will be very high or the permeability would be very low, depends upon the void ratio. So, a dense system will provide lot of hindrance to conveyance of a fluid. So, by virtue of this, a dense state of the material where the void ratios are extremely low, hydraulic conductivity or for that matter any conductivity is going to be less. Write down these concepts because these concepts are absolutely important, and unless you have understood this, there is no point in studying this subject, fine. On the other hand, when the system is quite loose, the void ratios are going to be very high, the porosity is going to be extremely high and the system becomes highly conducting. I am talking about only gas conductivity and hydraulic conductivity. Heat, current, electromagnetism are different processes, let us not confuse over there. Quick example of this type of structure would be the filters which you create in the swimming pools. Most of the filters are created by using granular material. So, there you wanted to filter the water. So, most of the filters which are used in engineering practices are made up of sand beds, single particle, clear. The second type of the structure is what is known as honeycomb structure. We do not call it as honeycomb, we say honeycomb, alright. So, honeycomb structure, and honeycomb structure is normally occurring in fine grained materials. So, by definition fine grained material would be less than 20 microns, fine, and this would be in silts and mostly the type of rock dust, rock floors. How it looks like? This is how it looks like. So, the chain of the particles or the grains which is assembled like this. So, what happens is due to very fine particle size, besides gravitational forces, the surface forces also come in picture. And I will show you in today's lecture what is meant by the surface forces. These are mostly the charges which are acting on the particles. So, finer the particle, the surface charges are going to be more. So, apart from the body forces, the surface forces are also playing an important role. They have very large voids, alright. Now, each of these cells is made up of numerous grains, numerous particles, alright. That is the beauty of the system. So, several individual grains, they come closer to each other and they form a sort of a cell. So, this is a cell, alright. Now, this is what is honeycomb structure is. These type of structures are very good as far as the load bearing is concerned. We were talking about the foundations in the very first lecture, clear. So, if I do investigation, if I take out samples, put the sample beneath the microscope, and if I see it the way I showed you last time, and if I can establish that this is honeycomb structure, I should not be very bothered, because this type of structure acts as a reinforcement. So, the load bearing is very good, and hence the volumetric deformations are not going to be much, alright. Okay, so, coming to the another type of structure, this is what is known as a flocculent structure. Flocks, I am sure you must have come across flocks. Mostly the fine grained soils, clays, alright, and clays are of the size 2 microns, typically 2 microns. So, this structure would have interparticle surface forces which play a very predominant role as far as the deposition is concerned. The mutual repulsion is very, very strong. However, this type of repulsion can be nullified if I inject some chemical into it, and that is the genesis of stabilization of the soils, which we were discussing in the previous lecture. So, stabilization of the soils can be done by injecting some chemicals which would nullify the charge, alright. Flock formation is an important thing, and these flocks, they act as independent grain. So, flocks are nothing but an agglomeration of particles which are clay sized, mostly bound together by the electromagnetic forces which are acting between the particles, and they create a honeycomb structure. These type of structures have high permeability, very high permeability. You can just draw maybe one element, I think that would help you. One unit you can just draw quickly, and rest is all a chain of the things. So, here when I say flock, so this is one flock. This flock, because of the electromagnetic forces which are acting on the surface of the particle, gets formed. There is a lot of hollow space inside. A person like good researcher would utilize this hollow space to inject something into it more fruitful and make this system very juicy. The next one is one of the ways of defining the very fine particles and the colloids. Colloids are less than 1 micron, and these are the ones which offer most of the significant properties to the soils. There are two types of structures normally we talk about. This I think I discussed in the last lecture also. The first one is known as a card house structure. Look at the orientation which I discussed last time. This is a platelet of the clay or the grain of the clay. Edge is meeting the face of the grain. So, this could be either edge to edge or edge to face. Edge to edge, I think I have not shown a very, this would do. I mean, this is edge to edge, you may say, this combination, alright. This is edge to edge. This is a beautiful example of how the face to edge is getting created in the settling process. So, anyway, so this part is clear, card house structure. Now, what I wanted to show you is that card house structure, if you compact the soil or if you apply some load on it, it gets converted to dispersed structure. So, the first animation should have been the dispersed structure. So, when you start from here and you compact the material, it becomes dispersed, more orderly, face to face. In geomechanics, these two are going to have lot of significance, and henceforth I will be utilizing these mechanisms to define how the properties of the soil mass change. Quick answer to your question would be permeability is dependent upon the porosity. Porosity is a fundamental property of the grains of the soils. So, if I take out this sample and of the soil, and if I want to see what is the porous space, that quantification is porosity. We will do it today, clear. And hydraulic conductivity is a mechanism, how easily water can pass through a matrix of soil mass. This is what I wanted to show you. If I take out one plate or one grain of the clay, this is how it looks like. So, we call this as a plate like or a flaky shaped. Look at the charges which come on this. So, the plate face is negatively charged because it is a very fine particle. So, the fundamental property or the fundamental charge is negative charge and it gets spread on the surface. On the edges you have positive charge. Where bacteria will come and sit on this clay platelet? Quick, where bacteria will come and form a bond? Mostly bacteria is negatively charged, alright. So, the chances are that they will be holding the clay platelets from the edges. So, there is something known as isomorphous substitution. Read about this much more, it is going to be useful for you. So, when I have a magnet like this in soils, the fine grained material which is clay, silica and alumina, if you remember we have talked about all these things in the mineralogy part, they get substituted by magnesium, calcium, lower valence ions, and that is what is known as isomorphous substitution. This concept can be utilized for creating calcium sandos. I did a consulting long back for making calcium sandos tablets. So, the concept is same. I would like to park different type of ions on a surface, and surface for me is a substrate. The technical word in today's language is substrate, and on substrate something comes and gets parked, adsorbed. Because of this, what happens is the system becomes unstable and the dynamics starts, alright. Now, the dynamics is nothing but cation exchange capacity, which makes the clays highly reactive. By definition, the cation exchange capacity of the clay particles is the capacity of these particles to exchange cations with the environment. So, suppose if calcium is present and sodium is available in the solution form, what will happen? Because of isomorphous substitution, the sodium tries to dislocate calcium, which it cannot do. Imagine a car cannot dislocate a truck which is parked in the parking space. So, these concepts are the order of the day. Those who are into R&D related to geomechanics and different subjects, they use these concepts quite a lot, creating different type of filters, liquid phase, gaseous phase and so on. The unit of cation exchange capacity is milliequivalents per 100 grams, and this is how the replacement series is. Alumina has a tendency to replace calcium. Look at the valence is 3, rest are 2 and 1, calcium, magnesium, ammonium ions, potassium, H ions, sodium ions and so on. So, depends upon what is that you are trying to do, where you are using these minerals, you can use them. At third year level, normally it is not expected that you should be knowing all these things, but as I am teaching to the masses and people who are interested in doing advanced courses on geoenvironmental engineering and process engineering, particularly chemical engineering related processes, for them this is definitely a must. Now, try to understand what is the concept of cation concentration in water. So, if you take clay particles and these clay particles, when they are submerged in water, there is something known as the gradient of the cation concentration. You have studied this in physics somewhere. Can you relate it? F is inversely proportional to R square at subatomic level. You have studied the concept of energy wells, is it not? So, these are the examples. I hope you can realize that at the interface of the clay particle there is a lot of concentration of cations, and this box which I have shown is known as a double layer. Geomechanics cannot be studied unless you understand the concept of the double layer. Double layer is the one which is the layer of cations surrounding the clay particles when the clay particles are kept in water. It so happens that apparently the size of the clay particle becomes 5, 10, 20 times. It is just like grapes, you put them in water overnight and what happens next day morning, they swell. So, this is what the concepts are. Lot of R&D is being done in this context to understand how the clay particles behave, what is the electromagnetic forces, and how the dynamics of the particles takes place when they come in different type of solutions. And if I change the concentration of the cations, or if I use different type of cations, what is going to happen to the equilibrium, alright. Beyond this boundary is all free water. So, adsorbed water is the one which is surrounding the particle of the clay, and this adsorption is because of the water being a dipole, clear. So, you imagine as if on the clay particles you have different dipoles coming together and the positive and negative getting connected with each other, and this is how the adsorbed water gets formed. It looks like a capsule. Sometimes adsorbed water is also known as hygroscopic moisture. That means you take the clays and put it in your laboratory or in your room, and Bombay city being very humid right now because of the rains, when you come back you will find that either it has melted, it has absorbed so much water, or it has become wet. So, this is what is known as adsorbed water layer, and I am sure you must be knowing the role of silica gel. So, what silica gel does? In your electronic items you normally keep a sachet of silica gel. So, what it does? Silica has a higher tendency to attract moisture and the vapors. So, you can safeguard your equipments because the surface area and the cation exchange capacity is going to be much more as compared to other minerals. Now, this concept is useful for those who might end up in advanced R&D, and otherwise also you should understand this is the clay particle, this is the adsorbed water layer approximately 1 nanometer of size. This thing is surrounded by a double layer of water, and double layer is the one which has lot of cations which are present in the system, and the whole unit is surrounded by free water. Some time back you were asking this question about the porosity and permeability. When we will go into the micro details of permeability, we will discuss all these concepts again, and we will discuss why clays are less permeable as compared to sands. By virtue of their mineralogy, the clay particles have a tendency to create an adsorbed layer of water, and two particles, when the adsorbed layer gets developed, now the pore space becomes so less that no fluid can migrate through it. However, this thing cannot happen in sands because sands are surface dormant, they are not surface active, there are no charges on them, clear. So, whatever we have been discussing about right now is all for very fine particles like clays.
So adsorb water layer thickness, like what is the what is the scale of thickness of adsorb water layer and double diffuse layer, if there is some general?
Good question. Normally double layers, as I have written here, less than 50 nanometers is very empirical. So, do not go by these figures. It will depend upon the concentration of cations, their valency, clear, number 1. So, I may modulate these layers by increasing the concentration of the cations and the type of cations which I am going to use, fine. So, a quick answer in third year classroom would be these are tentative numbers and they may change. Just to give you a comparison about the different clay minerals, I have used kaolin, illite, monzonite and chlorite. And if you look at the surface area, which is normally defined in meter square per gram, cation exchange capacity and adsorbed water of the minerals, you can make out that why some minerals are so active and why some minerals are so dormant. Sands do not come in the picture anywhere because their surface area is extremely low. It would be about 10-20 meter square per gram. You will realize that specific surface area is the one which guides CEC. So, if surface area is more, cation exchange capacity is going to be more, adsorbed water may be more or not. Do not try to remember these numbers, this is just to give you a feel of how the minerals look like. Monzonite, if you see, the surface area is extremely high, 800 meter square per gram. The other day I asked you a question, what is the size of a football field, if you remember. Cation exchange capacity is very high, water absorption is also very high. It is an obvious choice for people from different profession to use these minerals the way we want. Whenever you get time, please click on this link which I have provided to read more about how minerals behave. It is a beautiful paper on clay mineralogy, water absorption characteristics of clay minerals, but do not read it at third year level, alright. So, maybe keep these things pending.
If clay minerals have similar charges, then why do they have cohesive forces?
Why do they have some cohesive?
The cohesive nature of
Simple example is, you remember you were talking about this thing, clay particle is negatively charged, calcium ion comes from the environment, bacteria produces calcite, that calcium gets parked on the surface of the clay particle, clear. Two particles get bridged by a calcium ion, clear. Carbonate gets formed, carbonate deposition, two particles form a megalith. Megalith means they get stitched together, they get glued together, and hence cohesion becomes a way to demonstrate the shear strength. So, if you want to shear these two particles, it is difficult. Say two piece of papers, clear, and put a small drop of glue and press it a bit, and now try to tear it or shear it, it is difficult. The same thing is happening over here. Is this okay? You got the answer?